There are four electrolyzer technologies competing to produce the world's green hydrogen, and most people in this industry already have a strong opinion about which one will dominate. The problem is that most of those opinions are either incomplete or built on simplified comparisons that don't actually reflect how these technologies perform in real projects. In this video, we're going to do a full, proper comparison of all four: alkaline, PM, solid oxide, and anion exchange membrane. Not at a surface level, but across the dimensions that actually determine which technology fits which project. If you're developing a green hydrogen project, evaluating one, or financing one, the technology choice is one of the first and most critical decisions you make. That decision doesn't just affect the electrolyzer itself, it flows through your entire project. It shapes your capital expenditure, your operating profile, your degradation assumptions, your supply chain exposure, and ultimately your bankability. The issue is that most comparisons you'll find either oversimplify the discussion, saying things like PEM is better because it's more dynamic, or they dive so deep into electrochemistry that they lose practical relevance. What we're doing here is neither. We're breaking this down across 6 dimensions that actually matter: how each technology works, where it is commercially mature, how it performs, what it costs, how long it lasts, and where it fits in real-world applications. At the most fundamental level, all 4 technologies do the same thing. They use electricity to split water into hydrogen and oxygen. That's electrolysis. You have 2 electrodes, an anode and a cathode, separated by an electrolyte. Apply a voltage and the water splits. Hydrogen is produced at the cathode. What separates the 4 technologies is the nature of that electrolyte, and that one difference drives almost everything else about their behavior, cost, and application fit. Alkaline electrolyzers use a liquid electrolyte, typically potassium hydroxide, and this is a technology that has been around for over a century. PM systems replace that liquid with a solid polymer membrane, allowing protons to move through it. But this requires highly acidic conditions and expensive catalysts like iridium and platinum. Solid oxide systems operate at extremely high temperatures, 700 to 900 degrees Celsius, and use a ceramic electrolyte, fundamentally changing the thermodynamics by reducing electrical energy requirements, but introducing a need for heat. AEM, the newest of the 4, uses a solid membrane like PEM, but transports hydroxide ions instead, aiming to combine PEM's compactness with alkaline's lower material costs. When you move from fundamentals into commercial reality, the differences become even more pronounced. Alkaline is by far the most mature technology. It has been deployed industrially for decades at large scale, with hundreds of megawatts already operating globally. The supply chains are established, degradation behavior is well understood, and lenders are comfortable with it. PEM has rapidly closed the gap over the past decade, moving from niche applications into large-scale deployments, with major manufacturers delivering systems at tens of megawatts. It is now considered bankable, although supply constraints, particularly around iridium, remain a concern. Solid oxide is still earlier in its commercial journey. It works and its efficiency advantage is real, but it lacks the operating history required for large-scale financing confidence. AEM is even earlier, still largely in pilot phases with key uncertainties around durability and scalability. The takeaway is clear. Today, alkaline and PEM are the technologies you deploy, while SOEL and AEM are technologies you watch. Performance is where the trade-offs become more nuanced. Solid oxide leads on efficiency because of its high temperature operation, achieving electrical efficiencies in the 85 to 90% range. That's a significant advantage when electricity is your dominant cost input. Alkaline and PEM sit closer together, typically between 65 and 75% efficiency, with PEM often performing better at higher current densities. Speaking of current density, this is one of PEM's biggest strengths. It operates at much higher current densities than alkaline, which means smaller system footprints and higher power density, critical in space-constrained environments. Dynamic response is another area where PEM clearly leads. It can ramp from 0 to full load in seconds, making it ideal for coupling with intermittent renewable energy. Alkaline systems are less flexible, with minimum load constraints and less tolerance for frequent cycling, although newer designs are improving. Solid oxide, on the other hand, is not suited for dynamic operation at all. Its high-temperature ceramic structure requires stable, continuous operation and cannot handle rapid fluctuations. Cost is where most project decisions ultimately converge. Today, alkaline systems are the cheapest, typically ranging from $500 to $900 per kilowatt. PM systems are more expensive, often between $800 and $500 per kilowatt, largely due to catalyst and membrane costs. Solid oxide systems are even higher, reflecting their early-stage manufacturing scale and complexity. AEM doesn't yet have meaningful commercial cost benchmarks. However, cost is not static. PEM is on a steeper cost reduction curve than alkaline, driven by manufacturing scale and innovation, and could reach parity within the next decade. Solid oxide has a pathway to cost reduction as well, but it starts from a higher base. On the operating side, SOEL's efficiency advantage can significantly reduce electricity costs, potentially saving up to $0.50 per kilogram to $0.80 per kilogram of hydrogen depending on power prices. The challenge is whether those savings offset the higher capital and operational complexity. Durability and lifetime bring another layer of reality into the comparison. Alkaline again leads here with proven lifetimes of up to 100,000 hours and well-understood maintenance cycles. PEM systems are improving but still face challenges related to membrane degradation, catalyst dissolution, and corrosion. Current lifetimes are typically in the 60,000 to 80,000 hour range, with ongoing improvements. Solid oxide faces its biggest challenge in durability, as high-temperature operation introduces complex degradation mechanisms that limit lifetime. AEM remains the least proven, with lifetimes still measured in thousands rather than tens of thousands of hours. When you put all of this together, the application fit becomes clearer. Alkaline is the safest choice for large-scale, steady-state hydrogen production, where bankability and low risk are critical. PM is the preferred option for projects with variable power inputs, such as renewable integration or where space and responsiveness matter. Solid oxide is best suited for industrial environments where high-temperature heat is already available, enabling maximum efficiency. AEM is still in the future category, promising but not yet ready for bankable deployment. If you're evaluating these technologies for a real project and need to go beyond theory into actual numbers, your electricity price, your load profile, your location, that's exactly what H2 Hub is built for. It allows you to model PEM, alkaline, and solid oxide side by side using real cost and performance data so you can see what actually works under your conditions. The key takeaways are straightforward but critical. Alkaline and PEM are the deployable technologies today. PEM offers advantages in flexibility and power density, while alkaline leads in cost and maturity. Solid oxide brings efficiency but requires heat and still faces durability challenges. AEM holds long-term promise but is not yet ready for commercial deployment. Ultimately, the right choice is not about which technology is best in isolation. It's about which one fits your specific project constraints, your power profile, your timeline, and your financing environment. In the next video in this series, we go deeper into PM specifically, breaking down exactly how a single cell works, from membrane chemistry to water management and the real limits on performance. If you have questions about selecting the right technology for your project, drop them in the comments. We go through all of them. And if you want to follow the full series as it develops, make sure you're subscribed.